Hi, do you want to watch a video today? I want to watch a video today.
When a storm creeps in, it only takes a few minutes for things to turn ugly.
Well, there had to be at least 20 accidents, just like that. Honest to goodness, it was just a domino effect, domino effect, domino effect. I would calculate a minimum of at least 50 vehicles. This is chaos.
A pileup this big could take hours to clear. These drivers aren't going anywhere. These are the people doing their best to help avoid that chaos, fighting back at Mother Nature.
We do have it coming out both sides.
Before a storm even hits, brining is the first line of defense.
Merging into the 401 here, and hopefully everyone out there cooperates. I'm not out here to be your nuisance. I'm out here to save your life.
That stream of liquid is salt brine, a solution more efficient than dry salt alone.
This is dehydrated salt brine. This is what does the melting on the road.
Jeff Leach is an expert on highway maintenance.
The key point is that salt doesn't do anything. Salt needs to change phase from solid to liquid and become a brine. So first it has to dissolve, and it's the brine that does the melting.
Then come the salt crystals of different sizes. They work together to keep the ice off.
Oh, well, there you go. That's your information. I'm sure there's a ton of other videos to watch. It said Durham on that one truck. I don't know if this is North Carolina, like Raleigh, Durham, but some of the signs had some French on it, so it might have been Canada. One tiny thing I want to correct. He said salt has to change from solid to liquid. He didn't mean liquid. I mean, he said liquid. I think he meant solution, and that's what we're focusing on today. The buzzword of the day is colligative properties. And as it says there, you have your definition. We've seen some colligative properties already. We spent a lot of time in the fall talking about the fact that salt water conducts electricity and pure water does not. And that the conductivity of the salt water had to do with the fact that there were these solute particles, we didn't call it solute at the time, but we can now, was present in the solution. So conductivity would be considered a colligative property. The easy additional colligative property to observe is density. You see that with the grapes and the eggs, and it also seems like the fact that food coloring mixing is something of a density-related event, or maybe the salt has something to do with the fact that on the picture on the right here, this food coloring does not penetrate as deeply into the solution, or it doesn't penetrate as quickly. I'm not quite sure which is going on here, but it's clear to me that there's a difference in certain properties because of the presence of a solute in the mixture versus the pure solvent by itself. But that's not really what we're talking about today. What we're talking about today is salting the roads. And quickly as a review, I wanted to talk about freezing and melting in general, because it seems like the big problem with salting the roads, or not salting the roads with winter weather, is that when you get ice on the roads, obviously cars lose traction, accidents happen. So in all these cases, the same thing is happening. You have water, and it's being subjected, it's like at a higher temperature, and it's being subjected to a colder temperature. As we've said before, heat move is energy transferred because of a difference in temperature. And that heat moves from hot to cold, so you take your above freezing point water outside where it's below freezing point, and then what happens is the heat is released from the water, and then the water cools down. It reaches a lower temperature. Eventually, with that slower temperature, the particles move slower, average kinetic energy, right? As the particles move slower, their particle-particle interactions take over, and you get freezing to occur. That is to say that the interactions between two molecules, this hydrogen bond here, is now strong enough to hold the molecule still, where while it's moving faster, you're going to get some rotational or translational energy, and the particles just slide past each other. And that's what you're seeing here. These crystals that grow because the temperature is now low enough for the particles to lock themselves in that hexagonal, for water, crystal structure. So what does this have to do with salt? Well, one other colligative property that we haven't spoken about yet is freezing point depression. The definition's right there. Another way to represent the freezing process is shown here. Letter A and letter B both show freezing, but you can see these additional solute particles here. And the presence of the solute particles, you can see, has an impact. There's extra interactions. And because of those extra interactions, the waters that are present in a solution have a harder time locking in. And I'm not trying to personify it like it's some sort of active choice, but as the particles pass each other, that locking needs to happen. And if there's another particle in the way, the interaction can't take place. Now, this isn't to say that you can't freeze salt water. It still happens. But because of the extra interaction, minimum temperature for the solvent-solvent interaction to be a successful freeze is lower, which yields a lower temperature. That is to say, one way of thinking about it is that the solute has an interaction with the solvent, and that interferes with the solvent-solvent interaction, and it prevents melting from taking place until they slow down even more at a lower temperature. So it's not to say that the ice melts, or sorry, not to say that the salt melts the ice. It's that salt water has to be at a lower temperature to freeze. And it is true that when you freeze salt water, at least the first bits of ice that form are pure. The salt stays in the liquid layer until like the whole sample freezes, and then you do trap some ice when you get to really low temperatures. This is evident on certain bags of rock salt. You'll usually get a message on them that says, melts to a certain degree, where you're clearly stipulating if the outside temperature gets any lower than that, you'll still get ice. And that's the whole idea. We get ice outside when the temperature dips below 32 Fahrenheit or 0 Celsius. The addition of the salt means that you can go lower than that temperature and still visibly observe liquid water. This is good for roads because liquid water will run off the road. It's the solid water that's the problem because it stays put. Now that is also to say, there is a boiling point colligative property, but it's the opposite. The addition of a solute into a solvent to make a solution, you'll observe that the temperature at which the boiling occurs goes up. This isn't to say you should add salt to your pasta water to make it boil at a higher temperature. These changes for the boiling end of things are, fractions of a degree. It's a small amount, so don't walk out of here thinking that. But this does have an impact, and I have these images to help illustrate what happens when you add your solute. Notice here two things occur. So first, in a given sample, these two pictures are about the same size relative to the particles. When you start incorporating solute particles into your solution, there are fewer solvent particles present, like proportionally, right? If this is 100% solvent, this might be something like, it looks like 80 to 90%. And that means even at the surface of your solution, you're going to get fewer solvent particles escaping into the gas phase. This translates to say that a solution has a lower vapor pressure than its pure solvent. And that might help explain what's going on with the boiling point. If the boiling point is the temperature at which you reach that threshold vapor pressure, if the solution has a lower vapor pressure, then it's going to have to be heated to a higher temperature to reach that threshold. Another way of thinking about this is we saw on the previous slide that solute and solvent interact in the liquid phase. You'll notice here that there are no solute particles entering the gaseous phase here. They stay in the solution. And so there's an interaction between solvent and solvent, but there's also an interaction between solute and solvent. There's more interaction, and more interaction will make certain other things harder. That is to say, when a particle leaves the liquid phase into the gaseous phase, now there's two interactions to overcome. And if there's two interactions to overcome and there's stronger interactions because there's now more of them, that will hold the particles in the liquid phase with more force, meaning you have to be moving at a higher kinetic energy to escape that higher attraction. If you want to see this graphically, here are some pictures of vapor pressure. You'll notice that this right side here of both of these graphs looks a lot like Table H. I have a picture of Table H down here, and of course you've got your link to the reference tables. But you'll see that the vapor pressure of the solution is lowered relative to that of the pure solvent. If we say that boiling is the temperature, or the temperature at which vapor pressure is 1 atmosphere. You'll see marked over here 1 atmosphere on both the graphs. This would be our normal boiling point with the pure solvent. You'll see they meet right here at 1. At 3 is an increased boiling point. That's your change in boiling point right there, delta T sub B. And that, like you can see, it's shifted to the right because since the vapor pressure went down, you now have to increase the temperature even more to bring it back up to that 1 atmosphere. For the freezing, you'll see another line. I included both of these graphs because some solids have a slant one way and some have the other, but you'll see that regardless of the direction of the slope of the solid-liquid interaction line, this is a phase diagram for those who've never seen one before, you'll see that the 2 here is your normal freezing point, and there is a decrease in the freezing point, delta T sub F. You can see, I guess you sometimes see delta T sub M, but you usually do see T sub B and T sub F. But 4 here is your decreased because you have then weakened those interactions, so it has to be cooled even more to turn it into a solid. The way I refer to it, you can kind of see this picture, this represented in both of these pictures, is that the addition of solute to make solution stretches the temperature range of the liquid. For water, this would be like 0 degrees Celsius and 100, and then for your solution, you'd say like -3 and 101 or something like that. And that makes sense to me because solute-solvent interactions only take place in the liquid phase, right? Like I said, the solid freezes, it's a pure substance. The gas, of course, leaves the solute behind. So if you want to make sense of it that way, it stretches that temperature range so that the solute and solvent can interact even more, if that makes sense to you. One thing worth mentioning, though, once we're bringing numbers into the party, is the fact that if you make a 1 molar solution of various solutes, you don't always see the same freezing point. It's also true you don't see the same boiling point, but I don't want to laden you with numbers. But to look at this, this would just be a single example of a single solution compared to its pure solvent, where this is more, looking at several solutions. All of these are 1 molar. And I'll label these to be able to compare them back to the images that are below here. And you'll see in the case of like a 1 molar solution that obviously there's different temperatures. What's more interesting is that the decrease in temperature from A to B appears to be 2 times, and the difference in temperature from A to C appears to be 3 times. And there's some meaning behind that. In these images here, we've got 3 glucose, and here in this image we've got 3 sodium chlorides, and here in this image we have 3 calcium chlorides. But if you'll notice, the glucose doesn't split up into separate particles. However, ions, when they dissolve in water, we've seen this several times before, do. So you're going to end up with 3 sodiums and 3 chlorides. And then for calcium chloride, these 2 Cls, I know Cl2 as an element, is a diatomic element, but that's not what this is saying. This is saying we have the presence of 3 calcium ions and 6 chloride ions. So what's happening here is the amount of total solute is different based on the nature of the solute that we're using. Of course, sucrose is covalent, and sodium chloride and calcium chloride are ionic. You can pull all this information from the periodic table to make your formulas and understand what's going on, but the effective molarities of your solutes changes based on the nature of said solute. That is to say that for 1 molar sugar, you get 1 molar sugar. The amount of the total moles dissolved stays the same. For covalent substances, they don't split up. The molecules separate from each other, but the atoms in the molecules don't. For sodium chloride, the concentration of both the sodium and the chloride is 1 molar, so the total concentration of ions is 2 molar. And for calcium chloride, since there are 2 of those chloride ions, you get 1 molar calcium and 2 molar chloride, so that the total ion concentration for this solution would be 3 molar. And now, using these numbers, we can see an explanation for why the data shows what the data shows. The sodium chloride solution has a freezing point twice as low. The difference from 0 is twice as large because there are twice as many particles per mole as the sugar solution, and the calcium chloride is 3 times as much because there's 3 times as many particles per mole as the sugar solution. This is all, of course, saying equal concentrations of solute. Obviously, with a higher concentration of any of these, the effect will be amplified. So you could come up with the situation where like a 2 molar sugar solution and a 1 molar sodium chloride solution should have the same freezing point. And you can start to play that game if you'd like. Something that is worth mentioning, and I feel like it's important to talk about, is that this isn't all positive, right? Like you would almost say like, okay, why don't we just salt the roads all the time? Why don't we make the roads out of salt? Okay, maybe that's a bad idea. But maybe we should look for other salts too. There are some other ones that have more than 3 ions. One example would be like, I could think sodium phosphate, where you get 4 particles per mole. First off, that one's expensive, so like once we start talking about applications in chemistry, obviously money has to come into the discussion. But also, all this salt that we're putting on the road is dangerous, is damaging. You can see this image here that you have trees that are browning because there's too much salt. Plants have grown and evolved over time to experience their environment around them, and us dumping a bunch of salt out of place is going to affect that environment. You can see plant death. There were studies in 2014 showing that there's a large amount of chloride levels in the drinking water, and that's because of salting of the roads in the Northeast. Obviously, Flint doesn't have clean water, still, 6 years later. And one of the reasons is because high chloride ion content can strip lead out of pipes. Once it's stripped off the pipes and dissolves into water, it ends up in the drinking water supply. This is an example, unlike the previous video, where you're now seeing lead being there in a ridiculous amount. This is, of course, one of the ways that it gets into the pipes that we were talking about before. One other thing, not an environmental impact, but also the salt on the road does degrade the metal and the clear coat and the paint of cars, and you get to see this body rot that takes place. So there's a financial component too. And so for that reason, though salt does work, we're of course interested in alternatives that can help melt the snow, melt the ice, and get it off the road. One alternative doesn't rely on melting. If you've ever seen people use sand, sand can provide traction so that you don't slip on the road without melting the ice. Sand doesn't dissolve in water, obviously. Another one is ash. If anyone has access to a fireplace or a fire pit, the ash contains plenty of ionic compounds and a little bit of grit that doesn't dissolve in water, so it's really a good situation, and that's something that is at least a little more naturally occurring. And one thing I found in doing some research is beet juice is apparently being investigated and has been for some time. It has a calcium ion content that's relatively high as far as food goes. And obviously, if I'm using a naturally sourced ingredient and not just purified mineral salt and dumping that on the road, the negative impacts are somewhat lower. Obviously, if I'm transporting a lot of beet juice to an area that doesn't have beets, maybe I'll have an impact, but it should be lessened compared to just dumping salt. And one final note I did want to point out, it's not everything having to do with colligative properties is bad. I thought these two things were a little interesting to watch. The first one on the left, this is what happens when you throw a jug of water into an active volcano situation. On the top of the lava, of course, it's solidifying because that's where it's the coolest, but the incorporation of the water into the magma, lava, I can't remember which, the water, as long as it doesn't vaporize right away, gets incorporated into the crystal structure. And this is another example where water is acting a little bit more like a solute than a solvent. You can get these interactions happening, and it doesn't just have to be for aqueous solutions. The water getting into the lava lowers the melting point of the lava, magma, and you'll see way more liquid, way more activity. Yeah, there's some boiling water, but it's also causing some of that solid rock to melt because the temperature is high enough. It lowers that melting point. And then another one, I don't know if any of you have any experience, I've done a little bit of glass blowing. A lot of glass mixtures, it's based off of sand, silicon dioxide, but a lot of these sands will have solids mixed in, like borosilicates, or sodium borate, tetraborate, borax even, and the presence of these ionic compounds. If you mix 2 ionic compounds, the melting point of the mixture goes down. You get that interference. Even if they're not fully distributed like in a solution, you'll get interference at the interface of the two, and it will drive it down, where for pure sand glass you might need to get your furnace up to 2000 Celsius. The addition of certain ionic compounds can drive that melting point down into the 1500, 1400, even closer to 1000, which, if you are going through glass blowing or even industrial glass blowing, if you can operate your furnace at half the temperature, that's obviously cost efficient, it's safer for humans to be around. So there are plenty of examples where chemistry is helping us. There's some where it's hurting us, but then there's others where it's kind of beneficial too, just to give you a full scope of how all of these colligative properties are used around us. Thanks for watching.